Hello gang. In this section we're going to learn a bit about working with engineering metric notation. Time conversions we'll hold off until a separate lesson. We've already worked with scientific notation, so it's a pretty easy leap to go into another similar notation called engineering notation. The reason it exists is because we use metric prefixes all the time, especially for memory and processing speed. You hear things like terabytes, gigabytes, megabytes. And so we need to be able to switch easily between those. And mostly that's pretty straightforward, but we're going to get you familiar with all the metric prefixes and not just the big ones that are associated with computer memory. Speaking of computer memory, there's a pretty interesting article. This article is a few years old now, but of course there's a debate that may not ever be answered, and that is, what is the computing power of the human brain? From a purely mathematical standpoint, the author of this article, Wickman, seems to have a theory on this, and I'm going to put the link up for you to read this article. This isn't a required article, but if you read this, I would love to hear what your thoughts are on this. I would take an issue with one particular assumption that he's making in this article. So if you read it, send me what your thoughts are on this. And he tries to make a comparison between a typical computer's memory storage and the human brain. He arrives at somewhere in the neighborhood of 1 or 2 terabytes, maybe as high as 2 petabytes, but there's a lot of variation in that. But again, I think he's making some incorrect assumptions. Let me know what you think. But let's get started. So engineering notation is very similar to scientific notation, in that there's a coefficient as well as a power of 10. It works the same way. The only catch is the exponents have to be a multiple of 3. So here we've got an exponent of 6. As long as our exponent is a 3, a 6, a 9, or a -3, -6, -9, -12, then we're okay. The other catch is, since that exponent is more restrictive, the coefficient is a little bit less restrictive. We don't have to stay between 1 and 10 anymore. Now we get to stay between 1 and 1,000. That extra range for the coefficient gives us the ability to always make that exponent some multiple of 3. So let's write these 5 numbers using engineering notation. You already know how to put them in scientific notation. You already know how to write 494,200,000 in scientific notation. That would be 4.942 times 10 to the 8th power. But even though that's scientific, that's not engineering, because our exponent of 8 is not a multiple of 3. So we need to change that a little bit. We can write that as 494.2, since we have that extra flexibility with our coefficient, times 10 to the, and since we only had to move the decimal 6 places, that would be 10 to the 6th, which is a multiple of 3. And we've written that number in engineering notation. 0.000000593, we can write that in engineering notation. If we move that decimal 1, 2, 3, 4, 5, 6, 7, 8, 9 places over, this becomes 59.3 times 10 to the, we moved that decimal 9 places, and this is a very small number, so we're going to make that -9th power, and it's in engineering notation. Now, 6.83 times 10 to the 7th, that number is in scientific, but we want to move it to engineering. We'd have to focus on changing that exponent. We need to make that 7 go up to a 9. That would make our coefficient smaller, and we really can't go any smaller than 6.83 or we'll be too small. So we're going to make our exponent smaller, which will make our coefficient a little bit bigger. So we're going to change our exponent to a 6. Since we're dropping our exponent down 1 to a multiple of 3, that means our coefficient has to get 1 spot bigger, and it becomes 68.3 times 10 to the 6th. And we've got this in engineering notation. 27.23 times 10 to the negative 11. Well, there again, we need to change that exponent. We can go down to negative 12, which would make this a little bit bigger. Or we can make that climb up to a negative 9, which would make our coefficient a little bit smaller. In this case, we're going to have to make the exponent go down to negative 12. Since that's going down by 1 power of 10, our coefficient should get one spot bigger, and this will become 272.3 times 10 to the negative 12th. And the last one, 0.00820 times 10 to the negative 6. Now, our exponent is already a multiple of 3, but our coefficient is too small, so we need to make that bigger. If we move the decimal 3 places over, that would make 8.20, which is good. Now we're between 1 and 1,000. And since we made the coefficient 3 places larger, our power of 10 will have to get 3 places smaller. And we've gotten that number written in engineering notation. Okay, here's a little bit of practice for you. I've given you two numbers that are in engineering notation. I would like you to change them into scientific notation. Go ahead and pause this video, scratch those out, and play again when you're ready to see the solution. Okay, so if we want to write this in scientific notation, we need to make our coefficient smaller. It's too big right now. That's going to become 6.530. That's better. Times 10 to the, now what will our new power of 10 be? Since we made the coefficient 2 decimal places smaller, we need to make our power of 10 2 decimal places bigger. And that's going to mean we're going to climb up to an exponent of negative 7. 6.530 times 10 to the negative 7, that's in scientific notation. 20.7 times 10 to the 6th, not in scientific because our exponent is too big. Let's make that 2.07. Scientific has to be between 1 and 10 for our coefficient. 2.07 times 10 to the, since our coefficient got one spot smaller, our exponent has to get one spot bigger. And scientific allows us to use any number in the exponent, any integer that is. 2.07 times 10 to the 7th is in scientific. Is it possible for a number to be written in scientific and engineering notation at the same time? It is, right? If you happen to have a number with a coefficient between 1 and 10, and the exponent happens to be a multiple of 3, then that number is in scientific and engineering at the same time. Some numbers are in both. Most, though, are in one or the other. Okay, there's a lot of metric prefixes, and that's the whole reason we use engineering notation. Because anytime we write a number in engineering notation, that power of 10, which is I got an exponent of some multiple of 3, will have a corresponding name. If we have 10 to the 9th, we know that's a gigaunit. If we have 10 to the negative 3, we know that's a milliunit. So by putting a number in engineering notation, we're also kind of putting it into metric notation. You need to know for this course, one of the objectives is for you to recognize and be able to switch between metric prefixes. And so you need to know these metric prefixes. There are more out there, and you might know some of them from your other experiences, but these are the ones that you need to know for this class. There's a common one that I don't have listed here, centi, for centimeter. That's 10 to the negative 2. That's useful to know, but since it doesn't correspond with things related to computing technology, I don't require that you know that centi prefix, even though you might. You need to know from negative 9, 10 to the negative 9, which is nano, up to 10 to the 15th, which is peta. And so you'll need to spend some time studying those. So that when we get to our unit test, you can show me that you can switch between those, and that's what we're going to do right now. It's also worth noting that even though each of these is 10 to the 3rd larger than the one below it, in other words, it's tempting to say that 1 giga is equal to 1,000 megas? Strictly speaking, that's true. But when we talk about computer memory, as you may know, computer memory is based on powers of 2, and so 1,024 is actually that factor of change between the metric prefixes. Now, oftentimes that 1,024 is rounded off to be 1,000, and so depending on what company you're in, some people will take issue with that, some people won't. We kind of use them interchangeably and rely on context. So we would say that technically a gigabyte technically is 1,024 megabytes, but for the purposes of our work, the spirit of the metric prefixes is that they're just decimal moves in factors of 1,000, and so we'll always treat it that way. The examples I'm going to use in this course refer to units other than bytes of memory, and as long as we're talking about something other than bytes of memory, we always use even factors of 1,000. Okay, we're going to use a new term here called the best metric prefix. The best metric prefix is simply the one that replaces the power of 10 when we write something in engineering notation. So, for example, write these values using metric notation. Okay, 49.83 times 10 to the third volts. We know that 10 to the third is kilo. And so we would say the best metric prefix here is 49.83 kilovolts. 0.00045 meters thick. That's about the thickness of a dragonfly wing. If we put that in engineering notation, this becomes 45 times 10 to the negative 6 power. And if we replace that power of 10, this becomes 45 micrometers. You should also recognize what the symbols for each of these powers of 10 is, and so we'll call that 45 micrometers. That symbol is called mu, and we use that for micro because a lowercase m is already used for milli. Okay, at certain times of the year, Saturn is about 745,800,000 miles from Earth. We can put that in engineering notation. It becomes 745.8 times 10 to the 6th power, which is in engineering, and that, of course, becomes 745.8. 10 to the 6th is, you recognize that one? Mega. (745.8 megamiles). Now, usually miles are not used with the metric system since an imperial unit, but it is in fact true. We would call that 745.8 megamiles if we wanted to use the best metric prefix. Okay, our last one, when vegetables, fruits, and other products are harvested, they're not going to be perfectly clean, and surprisingly, the FDA allows 0.003 grams of mouse feces per pound when natural ginger is harvested. So let's put that in metric notation. 0.003 becomes 3 times 10 to the negative third. Now, if we put that in best metric, that becomes 3. We'll replace the 10 to the negative third with milli, and those are grams. And so we have 3 milligrams per pound. Okay, it's time for you to do just a little bit of practice here. Take a minute and make these 4 changes. Scribble them out on some scratch paper and resume playing when you are ready to see the solution. Okay, let's take a look at these. 500 nanoseconds. Well, what does nano mean? That means 10 to the negative 9. So we can say that that is 500 times 10 to the negative 9 seconds. We're asked to put that in decimal notation here, so that's a 9 decimal place move, and this is a very small number. So we're going to write 0.000000500. That shows our decimal moving 9 places to the left. And we have 0.000000500 seconds. 87.3 microfarads, that's a measure of capacitance or electricity storage in scientific notation. We know that that is 87.3. Micro is times 10 to the negative 6th farads, but if we want to put that in scientific, we have to change that coefficient. That becomes 8.73 times 10 to the, since our coefficient is getting smaller, our power of 10 is going to get a little bit bigger and go up to negative 5 farads. 2.5 times 10 to the second gigabytes in scientific notation. Well, that's 2.5. This is kind of scientific and metric mixed together. 2.50 times 10 to the second. But giga can be replaced by 10 to the ninth. And so now we can combine those two powers of 10 together into one. And this becomes 2.50 times 10 to the 11th bytes. And finally, write 9.22 times 10 to the negative 5th kiloamps using the most appropriate metric prefix. Lots of different ways to approach this, but one way is to say 9.22 times 10 to the negative 5th. Now that's a kilo, and so we can replace kilo with 10 to the 3rd. That's in addition to the power of 10 that was already there. So 9.22 times 10 to the negative 5th kiloamps. Let's put our powers of 10 together so that it's in scientific. That's 9.22 times 10 to the negative 2. Now let's get that in the most appropriate metric prefix. That negative 2 can go down to a negative 3. Then our coefficient is going to have to go up one spot, and this becomes 92.2 times 10 to the negative 3rd. Which is an engineering notation, and so we could say that that is 92.2, 10 to the negative 3rd is milliamps. And we're done. Okay, our last goal here is to be able to switch between metric prefixes. There's, again, a lot of different ways to do this. Here's one way to do that. We want to change 12 billion millimeters to kilometers or kilometers. So let's look at where we're at and where we're going. Milli, that's 10 to the negative 3rd. Kilo, that's 10 to the positive 3rd. So we know that we are changing our power of 10 from negative 3 to positive 3. That means that we are gaining 6 powers of 10. And if we're making our exponent go up by 6 powers, our coefficient is going to have to go down by 6 places. And so if we do that, we'll move our decimal 1, 2, 3, 4, 5, 6 places. This becomes 12,000 kilometers. And our last one, 3.7 times 10 to the 8th nanoamps to megaamps. Where are we at? We're using nano, which is 10 to the negative 9th. We want to get to mega, which is 10 to the 6th. So we are climbing up a total of 15 spots from negative 9 up to a positive 6. If that's going up by a factor of 15, then our coefficient here has to go down by a factor of 15, which means this is going to become 3.7 times 10 to the, if we lose 15 out of our exponent of 8, that becomes negative 7, and those are now mega amps. Okay, that wraps up this section. There's a corresponding Blackboard assignment dealing with engineering and metric notation that has been assigned. You can go ahead and do that now. As always, if you have any trouble with this topic, be sure to stop by the Learning Commons or drop me an email, and I will certainly help you out.